Hello and welcome to EVEG 2000. I'm sorry that I can't be here to meet with you all this week. I'm currently in Atlanta for an ACS conference. I'll be traveling back on Thursday, probably the time you'll be watching this lecture. And so I'm unable to give Tuesday's lecture in person. I'll be giving a conference presentation, doing the conference sort of thing, and then on Tuesday and then on Thursday I'll be driving back from Atlanta. So my name is Samuel Snow. I've been a professor here at LSU for about 5 years now, since 2006. Primarily I've been teaching the water and wastewater treatment class EVEG 3110 and a similar class 4156, which is water and wastewater treatment in developing countries, along with a grad class. Now, typically, I've been teaching the water and wastewater treatment for the civil engineers and any other majors that want to join. So I'm excited this semester to actually be engaging with you guys, the EVEG crew. Looking forward to meeting you, getting to know you guys a little bit when I come back from the conference. A little bit about myself real quick. As you can see, I'm probably on the younger side of the faculty. I am 34. I did pretty much all my schooling at Georgia Tech. My family's from Georgia. I grew up in Georgia, stayed there for school. Georgia has a similar program to TOPS, and so I took advantage of that and then decided to stay for graduate school. From there, I spent a couple years in Michigan after getting married and ended up working for a couple years, working up there for a couple years. Part of the time I was at the Michigan Department of Environmental Quality as a permit writer. Then I decided to come back to academia. I did a postdoc at Michigan State University before I was hired here at LSU. So since being here, I've been actively doing research, mentoring students, learning how to teach, learning how to do the professor thing, and I've certainly enjoyed it so far. This, however, will be my first time teaching EVEG 2000. So in case you were wondering what that even means, what EVEG 2000 is, this is Environmental Engineering 1, according to our course schedule booklet. And really this course is about really training you to have the fundamental skills and understanding that really drive how we understand mass balance and materials balance in environmental systems. So today I'm going to be going through the syllabus with you, going to go through a few broad, big picture notes. I'm also going to show you how I plan to lecture in class. It'll look a lot like this, except I won't be comfortably seated in my chair, but I still will have my handy little writing pad, my cool little half glove writing pen, and I'll be standing at the podium with a laptop, and I will broadcast like I'm doing now, except it'll be broadcast live on twitch.tv/snowslab, so that if anybody's sick or quarantining or perhaps can't make it to class, you can watch live on that format. I will also take these lectures and upload them. Any notes that I take while lecturing will appear as well on Moodle. I will post a link to the a YouTube link for the lecture like I'm doing now. It's also going to be available, though, the lectures will also be available pretty much immediately after on the Twitch website, but YouTube will caption them for us, and then I'll get that permanent link uploaded. I will also post these slides with the notes like I just said, and so that's kind of what you can expect from the typical class. I wish I could be live with you right now in case you had any questions, but we'll cover them when I'm back in person with you. Okay, so that's just a quick little bit about myself. Coming back to the class, we'll go through the syllabus in a moment, but I want to give you sort of the big picture, why we care about mass balance and what that means, and really how to think about environmental engineering in a very broad sense. Really, environmental engineering is always looking to balance human needs versus environmental needs. And when I say environmental needs, really what I'm talking about is humans, like we people, we like having a functional environment that is performing well, it's sustainable, it's healthy ecosystems, we're not destroying all sorts of things. But at the end of the day, what we really need is often protection from the environment. Fortunately, a lot of us have that completely covered. We've got all the food, shelter, water, all of that, in a kind of a developed country or in a affluent area. Those are not usually problems. But if they are a problem, then you're sort of fighting against nature. As these basic components become less of a problem, then we're realizing, then we have the capacity to see, oh, well, we also like nature for all sorts of reasons, and we want to preserve it. So environmental engineering takes that dilemma there and aims at preserving environmental systems, mitigating human impacts on them, and while also protecting humans from any environmental hazards like pathogens in drinking water. So it's really a balance there. And the way we deal with pollution or understanding how something in the environment can go wrong or can be ameliorated, something that can be fixed, disinfected, something like that, is we're almost always talking about some sort of mass or material that is either transformed or transported through some process that we design. Or maybe we're just studying how it occurs in the natural environment. And that gets more towards the quantitative environmental science disciplines, maybe understanding how some minerals exchange and evolve on the earth, or different natural processes like that. So in terms of the engineering side of things, we can think of environmental engineering as having some sort of media. Maybe that's water, maybe that's air, maybe it's water that's inside soil, so it's pores. And then we have some stuff in that water, in that media. And that stuff is what we're interested in or concerned about. And so when we have this stuff, maybe it's liquid with a bunch of pollution in it, then we're going to send it through some sort of process. And what that process is going to do, maybe it's going to transform, maybe it's going to separate, some sort of mass transfer or mass transformation to give us perhaps clean water, maybe with a little bit of contamination that's not a problem anymore, and perhaps a little pile of the stuff that we can go landfill or that we have otherwise collected in some manner that then we can deal with more easily. But essentially what we're doing here is taking stuff that's in some media, sending it through a process, and transforming, transporting, doing something, some sort of manipulation to that stuff. So in that sense, almost all of environmental engineering has to do with these mass balances. So that's what a lot of this course is going to focus on, is really diving deep into how to understand these mass balances, how to compute them, what kinds of units, conversions we need, really train you, prepare you to do, to go deeper into more advanced biological processes, more advanced chemical processes, these different things, water treatment, for example, all these things that we want to really be able to understand how effective our process is. And it's all coming down to the principle of conservation of mass. So that's essentially the basis of almost all environmental engineering. Now, that's going to be our focus. I will add here that in addition to mass, there's also consideration for energy, which is in some ways related to mass. And a component of environmental engineering does deal with energy balances. We're not going to deal directly with that this semester, but it's certainly another component, especially if you're looking into energy fuel systems. Okay, what we're going to look at is really three media. So mass balances in soil, water, and air. And a lot of times you'll have all three all in one place. So here's a picture where we've got this muddy soil with water oozing out of it. This is kind of pore water in a salt marsh. And we've got air interfacing here too. So it's kind of all three interfacing. So it's important that we can identify what are the tools to understand where the water is going, what's happening in the water, maybe it's dissolved oxygen that we're interested in this system, how much dissolved oxygen is in that water on top, how much then is in the pores below, how deep do you go before there's no more oxygen because of all the biological processes going on. There's all sorts of complexity all in this little snapshot. We're going to take a very big picture overview of little pieces of stuff today, and then starting next week, what we're going to do is start walking through the physical processes, and then the chemical processes, and then biological processes. So we're also going to take a look at air quality and, well, more accurately, how to deal with mass transport in air for atmospheric purposes. So we see here this massive plume from a forest fire. Incidentally, I actually took that picture. This was some time ago when I was in college. I had an internship in Seattle, and I was climbing a mountain with some friends. This is Mount Adams in Washington. And it just so happened that day, a massive forest fire broke out pretty close to our campground. So right around the time we were summiting, it just really sprang up in full force. So we had a very scary, but fortunately uneventful trip back down to our camp, which is probably somewhere around here. So that was quite entertaining in retrospect. We're happy that nothing bad came of it. Okay, so I mentioned just a moment ago, we're going to take a look at these transport and transformation phenomenon in three ways, essentially. In the physical realm, which would really incorporate diffusion, advection, and stuff like mechanical erosion, some other processes that are just physical in nature, maybe using gravity for sedimentation, understanding the physics of particles descending through water. We're going to just get a grasp of important units and equations for different physical processes dealing with mass transport. We'll introduce some basic mass balances at that point, and then get a little more advanced with the mass balances with chemical processes as we start adding some things about the rates at which something is changing. Now, you can have a physical rate of change, some physical process causing a physical reaction, or you can have a chemical reaction. So a physical reaction would be two particles stick together and form one particle. So if these particles stick together and now they are one aggregated particle, you could call that a physical process, and then maybe they sediment down faster. So something like that is an example of a physical process, whereas a chemical process, you probably can think of a lot of chemistry. Maybe an explosion is a chemical process where bonds are liberated and a whole bunch of energy comes out, oxidation occurs, releases lots of energy. Some examples of chemical processes in the environment would be photochemical reactions happening in our atmosphere. We also use photochemistry quite a bit for specific water treatment technologies, ultraviolet light driven things. We can also look at geochemistry, so the kind of the chemistry of natural waters. How do minerals play a role in natural chemistry of waters? How do we manipulate the dissolution and precipitation rates to, let's say, remove iron or arsenic from water? Stuff like that becomes very relevant. So we're going to get into some chemical processes. And again, we'll focus on the basics, remind you of the things that you learned in chemistry some time ago, and then start helping you to apply those to real systems and get a feel for how you're going to use these moving forward with this degree. And last, we'll cover biological processes. This will be dealing with things like bacterial growth, decay, and how we can use them to transform waste products in water into either harmless products or possibly even useful products. So we're going to dig in a little bit to how we talk about those systems the last portion of our class. Okay, so speaking of the class as a whole, I expect to give you 2 midterm exams, 1 final exam. The final is not going to be comprehensive. Hopefully you've already taken a look at the syllabus. We'll take a glance through it ourselves here in a moment. But currently, my plan is to have the final exam will not be comprehensive. It'll just be essentially equal to the midterms. And it'll be those 3 components, that physical process, the chemical processes, and the biological processes. Now, I say it's not comprehensive, but in truth, a lot of the things we're learning all throughout are going to apply. So you will do well to be proactive in learning the fundamentals here so that for each of the following sections, you're better prepared. So in some sense, it's cumulative in that you're building these skills and you're going to be using those same skills throughout. We will have participation quiz type activities. A lot of times these will be Kahoot. Sometimes, and I'll show you that in person, guide you through that if you haven't used it before. It's a website that allows us to use our phones to just have an interactive quiz type of situation. These are going to be low-key. Most of the credit grade-wise will be given to you simply for participating and being in class. And about 1/3 of the credit will be a challenge to you to make sure you get the right answers or thinking in the right direction. So that's what you can expect. May not be every class period, but probably fairly frequently. And occasionally I'll do something on Moodle instead of Kahoot, likely, to give you a little more time, or maybe something that's slightly more involved. But the same thing will apply. You're going to have most of the credit for simply participating. And then a portion of it then is graded. Our textbook here is, for the class, is this Principles of Environmental Engineering and Science by Susan Maston and Mackenzie Davis. This book seems to be good. I've not used it before, so this will be my first time making use of it, but I think it will serve us pretty well. So again, bear with me if my preparation in terms of my familiarity with the book slows us down a little bit. I do apologize, but I expect it not to be too big of an issue. Okay, so I'm going to pull up the syllabus now, kind of walk you through that for a moment. Okay, so hopefully you've taken a look on Moodle and found the syllabus already, but if not, here you go. My plan is to have office hours every Tuesday, and I need to clarify that. I'll update the syllabus accordingly, but this should be, Thursdays at 11 a.m. in my office, or we can always Zoom by appointment, or potentially meet in my office by appointment. Class time, you should know already, is 3 o'clock Tuesday, Thursday in Turode Hall. I've got a link here for the Twitch page. Normally, I'd be live right now on Twitch. Instead, I'm just recording this in advance. Okay, textbook, I talked about that. We've already gone through the course overview. Can take a read if you want some more specifics here. Course objectives. There are certain things that our department is aiming for you to learn and be equipped to do with this class. So this is describing those. And if you take a look, basic engineering calculations apply to a multitude of environmental engineering problems. So that's where we're looking at the air, water, and maybe even soil type problems. Soil is usually a water type problem, but there is an interface. It's different if you're interfacing water with solid versus water with air and stuff like that. But anyway, the point being that you can apply the basic concepts to a wide variety of systems. You'll develop an understanding of what an environmental engineer is and does, and kind of identify the areas that you might be able to work or that an environmental engineer would work. You'll have these tools for system analysis and system design, specifically mass balances. And we're also going to work on understanding of data analysis tools. So I will be challenging you to use Excel spreadsheets. I'll also give you some training in that regard. I've used Excel for many years. I know that for you, it's probably a little bit hit or miss in terms of comfort level. Some people just end up using it for different projects or school assignments or whatnot. And I find that tends to be pretty variable, but what's not variable is the utility of being comfortable with Excel. So we're going to work towards that, improving that as a skill for you. And then of course, all of this should be helping you develop critical assessment, critical thinking skills, which will serve you for life. Okay, grading is fairly straightforward. My plan is to have each of the exams count 100 points out of 500 total. So that's 3/5 of the total class are exams. 1/5 then would be your homework assignments, which I expect to have about 5 for you. And then the last 5th will be class participation. Grading scale is pretty standardized here. Please take a look at the homework and exam policies. If you do have any questions, the details in there should be helpful. If you can't find your answers there, please feel free to ask. But I do appreciate it if you look there first. Chances are it's answering some of the questions you might have. So as far as I understand, LSU is going to hold pretty much all classes in person. So in light of that, we're going to be doing exams in person unless there is a specific exception, and I'll work with you for that if needed. Talked about class participation and attendance. I do expect you to be in participation and attending. I expect you to be paying attention to Moodle. This is a way that I communicate with you. I might post things. I'll mention them in class. I might not always remember to email you when I've posted a homework, for example, but I do expect that is up to you to be tracking with the course, understanding what's happening when assignments are due. And typically you'll get a good feel for that just by simply attending class, listening to the lectures. But Moodle will be there, assignments will be posted there as well. Of course, academic dishonesty will never be tolerated. The expected schedule, as you already know by now, there's no class for the first session. This recording is what I've designed for the second session. I do expect you to do the reading assignments that I've posted to Moodle and that I've described in my email to you. I'm going to talk a little bit more about those in a moment, but my intent is for those to give you a good picture of what this whole field is like and what kinds of questions can we answer and how would we go about that with the tools you're going to learn in this class. So I mentioned earlier that we're going to go to the fundamentals of materials balances in general, how that applies with physical processes, chemical processes, and biological processes. Now, given that this is my first time teaching this course, I'm not super confident that it's all going to work out precisely as I've written here. This is my best estimate right now, but I'm going to be asking you to be flexible with me because I'm sure that some things will have to be revised eventually. I will work in time here to add perhaps mini lectures on using Excel, demonstrating different tools, techniques, and tips for you. Okay. So with that, the assigned reading, there are 2 articles, both in the Journal of Environmental Science and Technology. These are both were published shortly after the Deepwater Horizon oil spill. And the reason I'm drawing your attention to this, and both of these actually are comparing the Exxon Valdez oil spill to the Deepwater Horizon. I have both of these up here. This first one by Charlie Schmidt, this is actually a perspective article. So this is not really digging too deeply into a specific highly technical topic. It's a little bit more of an overview, and if you look, it's really just one page. And I found that the related content, these related articles were interesting, and I selected one, I think it was even the first one, seemed most relevant to me in terms of giving you a little bit deeper of an idea of how these two spills were different and essentially how and why they were different. So as you will see, the physics, the biology, and the chemistry for these two different spills, even though you might think of them as both as massive disasters, it turns out that outcomes and long-term effects were vastly different between the two oil spills because the environments were so different. And so what I hope that you can take away from these, and we'll perhaps have a little bit more discussion in class, perhaps a participation activity on these, I hope that you can take a look, and again, even this one, it is more technical, but it is not overly technical. So I do expect you to be able to read through it and gather some information from it. I think it will be interesting. And as you go through it, what I'd like for you to do is to really think about the different aspects playing a role in terms of the environment. So you have to consider the soil, the water, and the air, and the physical, chemical, and biological processes involved in those media, and how all of those parameters and factors come together to kind of dictate what the fate of the oil is going to be. And keep in mind, by the way, the Deepwater Horizon, that was an enormous amount of oil that spewed out into the Gulf compared to the amount of oil that the Exxon Valdez spilled. But take a look, find out for yourself which one was effectively worse, or in what ways was one worse than the other. Okay, so time for the big picture overview with a few examples of what we're going to see in the future in the class. So I mentioned before, the mass balances are really the thing for the class, and essentially the thing for environmental engineering, although we will get more specific in other classes, whether it's biological or chemical, and so on. So units then, so when I say units, I mean, if you say, oh, I weigh some number of pounds or kilograms, the pounds or kilograms, let's just say 150 pounds. Someone might weigh about that. If you convert that to kilograms, how do you do that? How many kilograms is there? So when I say units, really what I'm talking about are the units, that number, or that specification we add on to the end. You could say grams, or you can say kilograms, you could say milligrams, and perhaps you could even use that type of prefix to pounds, although that's not a metric unit, so it's not we don't really do that. But you could go tons, right? You could go 150 tons or ounces or some other unit of weight. And by the way, these are not exactly the same. This is a unit of weight. This is a unit of mass. We can relate them directly on Earth, but if you take 150 pounds and say 150 pounds on Earth, that's different than 150 pounds on Mars because the gravity is different. So, but the mass would be the same if you said 150 kilograms. Anyway, point being, these units are essential, and it's very important when we have to convert units to make sure that we're doing it properly and we're doing it methodically. So it's very unfortunate that the US uses a system that is not metric units. And I say that's unfortunate because a lot of the world does, and metric systems generally make more sense. And so there's a big opportunity for confusion if you ever have to work across these. So it's very important that we are able to get it right. And there's also, even if everybody did use the metric system, you still need to deal with unit conversions because some measurements can only be made in some sort of unit, and then you need to convert. Chemistry, for example, oftentimes we have to weigh something to get a mass, but in terms of the chemical reaction, it actually matters what number of the molecules you have, so you have to convert to the number, which is that molar units. So it's really essential that we can get a precise, careful, and thorough handle on understanding units, understanding unit conversions, so that we can even begin to talk about a materials balance and even assume that we could get it right. The other thing that units are great for is if you forgot how to solve a problem. Units can often tell you where you went wrong or how to do it right. Maybe you forgot a formula. Maybe you forgot some conversion or something. Well, if you write down the units and you track them, chances are good that you can think your way through the problem based on those units. Okay, so mass balances, almost always what we're going to talk about when we talk about a mass balance is not just simply, 5 kilograms and hey, that's the same thing as saying 5,000 grams, so they're equal weighted. No, normally what we're talking about is how mass is changing over time. So what we're talking about is how much mass is traveling through a river over, per second or per hour, something like that. How much, to use maybe a different concept here, how many pennies are added to this pond that people are throwing in, what mass of pennies per time. Sometimes we might do it in number instead of mass. Sometimes we might be using a concentration, but that ultimately ends up being mass or number there as well. For anybody that might be doubting your memory of chemistry, units help here too, because almost all of what we do with chemistry is all about those units. We will go a little bit more advanced, prep you for some of the chemical equilibrium equations that we're going to need in water treatment. But we'll take our time there and make sure that you are well equipped to do so. Of course, I expect you already have some familiarization with dealing with concentrations, how to do mass balances, or excuse me, how to mix two liquids to find a new concentration. We'll take you through that as well, give you any review that you need, and make sure that you're confident there. So one thing that I will do once I am back and can be there with you in person, is I'm going to do some sort of a in-class activity to see how comfortable you are with these different topics. But that's going to have to wait for next week. Okay, so there's some basic SI conversions, so metric standard units here. You should probably know these, or at least most of them, right? The millimeter, milligram, that milli is that prefix, it's lowercase m. There's micro, there's nano, there's even pico and femto. I would expect that you ought to be familiar with at minimum the centi, milli, and micro. With this class, I hope that you then are also familiar with nano. Definitely should be familiar with kilo for like kilogram or kilometer. Probably should be familiar with mega as well, which is 1 million something. Certainly be ready to be using these conversions, is what I'll say here. So this is, kind of one of the simplest types of conversions we can do. If you have 1 meter, then 1 decimeter is 1/10 of a meter. If you have 1 decameter, which I don't think I've ever seen somebody use that, but you could, that would be 10 meters. So that a decagram would be a DAG. Most often you'll see stuff like kilograms, kg. you've seen this before. I'm going to move on from there. So when I give you exams, chances are good, if we're doing anything with water, I'll probably give you this specific table. And the reason I want to highlight this right now is to show you again an important aspect of paying attention to units. So if we're ever doing a problem where the density of water, or even air for that matter, is important, and you have some sort of density lookup table because the density changes as a function of temperature. So we have temperature here, and we have different densities, and therefore specific weights and viscosities, all these things. What I want to draw your attention to here is the units. So the unit for density is kilograms per meter cubed, at least in this table. You could also do grams per milliliter, for example. And converting between those two is something that you'll need to be able to do. Now, another aspect is how important is it to check the units. If you were to give me the density, read off the density for 25 degrees Celsius water, you would take the 25 and you're looking over here, you know this is the density, and you say, aha, here it is, okay. So the density then is equal to 0.89. If you gave me that on an exam, well, where are the units? That's entirely wrong, because you haven't specified what these units are. Excuse me, I said density, I meant dynamic viscosity. And don't worry about dynamic viscosity. You'll learn more about that in some other course, and we'll touch on it as needed here. But what I want to show you is this table's giving you these units, and it would be very easy to miss the fact that within these units, so you have kilograms per meters per second, but in addition, you also have times 10 to the minus third. So this is not 0.89, this is 0.00089 kilograms per meter per second. So that would be the correct answer, but it would be very easy to get it wrong if you happen to not write your units. And you see, if you look in here for this kinematic viscosity here again we see this multiplier within the units here as well. So I'm just drawing your attention to this because it really is important to be giving attention to units. You would do very, very well, and probably it would be an automatic pass for this class if you simply gave yourself the discipline to write out your units as you work problems. I understand that sometimes it just gets cumbersome, and I'm going to leave it up to you for your scratch work. But if I were you, I would at least write them once the first time you're writing or you're filling in a number, and at least the first time and the last time, so that you make sure that you know what you're starting with and know what you're ending with. Better yet, keep the units throughout and make sure that you're not doing something that's violating unit balance. You're not equating kilograms to milligrams, because you have to have a conversion there, obviously, to relate the two. Okay, so there's going to be some unit conversions that I just simply expect you to know, a lot that I will expect you to be able to derive or that you are going to learn over the course of the class. Just kind of a little example here is going to be the conversion from liters to cubic meters. And this is going to apply to both liquids and gases. Well, really anything you would measure liters or cubic meters. So this is volume units here. So 1,000 liters is 1 cubic meter. That would be a very good fact to keep in your mind. And the reason that would be a good one is because you can do a lot from there. Because then if I ask, okay, well, how many milliliters are in 1 cubic centimeter, you could actually potentially solve for that given the different conversions. And here I show you that 1 milliliter, there is 1 milliliter in 1 centimeter cubed, 1 cubic centimeter. We can derive that if we were to take that 1,000 liters equals 1 cubic meter, and then we were to take a look, well, how many milliliters are in 1,000 liters. And how many cubic centimeters are in 1 cubic meter. And we could go through that and essentially derive this portion here. Now, the important thing is when we convert a cubic, that cubic has to be converted properly. So I'm just going to focus on that for a moment to demonstrate why, on the one hand, it's liters to milliliters, on the other hand, it's meters to centimeters, and we have such a big difference. So 1 meter, I'm gonna relate the meters and cubic centimeters here. So we're gonna say how many cubic centimeters equals 1 cubic meter. Well, we know that we have 100 centimeters equals 1 meter. And we know that because we have over here centi is 1 in 100. So we know that from our table over here. Now, in order to convert it with a cubic, what we have to do is we have to cube both sides, right? So we cube over here and we cube over here. Now, the really important thing here is that we cube outside of the number in here. So when we do that, we end up getting cubic centimeters, but we also get 100 cubed. That's the difference here, and that's really important because then that means we have 100 times 100 times 100, that many cubic centimeters equals 1 cubed is still 1 cubic meter. So that right there explains why we have 1 milliliter in 1 cubic centimeter, even though we had 1,000 liters in 1 cubic meter. Because that difference here is you divide that by 1,000 to get to milli, 1,000 liters, that you can fit 1,000 milliliters in 1 liter, you multiply that by another 1,000 to get into 1,000 liters, that's your 1 million. Okay, so I say all that to give you an example of the types of unit conversions that probably you already realistically know this, but this way you'll be able to get, we're going to practice this directly and as explicitly as we can. So a challenge for you then would be to take that previous lookup table here and answer how many grams are there of water in 1 milliliter if the water is at 5 degrees Celsius. So you can take a look at this, this chart, this table, 5 degrees Celsius, you have some density, and then you could get some answer for how many grams are there in that 1 milliliter at 5 degrees Celsius. It turns out, pause this if you'd like to go ahead and try this yourself, but one way we define the weight of a gram is actually the weight of 1 milliliter of water, if it's at that 5 degrees Celsius. So it's actually 1 gram equals 1 milliliter. And you could derive that from these units, taking a look and saying, okay, 1,000 kilograms per cubic meter, and then converting from those units into grams and milliliters. Because this is, if you divide both sides by milliliters, that's one essentially gram per milliliter. Okay, so there's another type of unit conversions that you'll need to become familiar with. We're going to cover this in more depth later, but just as a reminder is that number to mass conversion. You've seen this before all the time in chemistry whenever you took chemistry, and that's those molar units. And this requires some ratio. how much does one atom of lead weigh compared to one atom of helium? Well, helium is very light. So if you have 10 atoms of helium versus 10 atoms of lead, there's going to be a much bigger difference. Or there's going to be a very big difference. And you can kind of think about that. You've felt different objects that are made of different stuff, and some are more dense than others. You can also think about this in terms of that number conversions. So I used the example of 10 a moment ago, 10 atoms. Well, a mole is just like saying 10 atoms, except it's a lot more than that. It's 6.02 times 10 to the 23rd atoms. So in a way, that the whole molar system is just like using a dozen. It's like a dozen atoms or a dozen eggs, right? So you could weigh the mass of a dozen eggs and compare that to a mass of a dozen cars, okay? So if you were thinking then about kind of how many eggs does it take to egg a car, for example, which I'm not recommending you do, then you can see very clearly that the number ratio is perhaps more important than the mass ratio. You're not looking at, okay, well, we have 10 tons of cars, therefore we need 10 tons of eggs. No, you have 2 tons of cars, maybe that's 2 or 3 cars total, and so you need at most a dozen eggs per car, something like that. It's a numbers basis that's actually the important part here, to use a very silly example. So we'll revisit that when we get to our chemistry section, but I wanted to just remind you how we're using units to talk about this mass and number, essentially materials balance equations here. Concentrations come in all shapes and sizes. I just threw my pen across the room. Oops. I'll get that in a minute. But concentrations essentially are different, you can have different types of concentrations. It can be a volume basis, so you have some volume of liquid or air or soil, and then you have some mass or maybe some number or some, maybe even a volume per volume. So you have an entire volume of air in this room, and a little pocket in the corner is what we would say, all of this is oxygen that's spread out in this room, and the rest of it's nitrogen. So you have some volume per volume basis. So you can look at volume, you can look at mass, you can look at percentage, all these different ways to talk about the way you're defining a concentration. And at the end of the day, it's an amount of stuff in an amount of other stuff, as I've so scientifically demonstrated up here. So we'll end up talking about and working through what it means to have a part per thousand, part per million, part per billion. And essentially, you already know what that means, you just don't know it yet. Because a part per thousand is a lot like a part per 100. And a part per 100 is just your standard percentage. So literally what percentage means is parts per 100. So let me grab my pen to demonstrate that. So if this symbol, which you're all familiar with, is parts per 100, then 5%, 5% equals 5 in 100, right? There's 100 total units or things. And 5 of those are what you're interested in. If you had 5 parts per 1,000, we'll use the parts per 1,000 here, which can get confusing if you're dealing with parts per trillion, which also is PPT. Then that's 5 in 1,000. Simple as that. So, and in fact, sometimes that will use the same symbol as percentage, but with an extra 0 there. So 5 parts per million then, ppm, you'll see ppm quite often, is 5 units in 1 million. Simple as that. So you already kind of know that, but we'll get practiced in using that in different systems. Okay, so I mentioned the egging a car as an example of how to deal with mass versus number calculations. That's exactly the same things we'll be doing with a mole. Again, you can think of that 1 mole of X is like 1 dozen X. It's just a difference. Instead of 6.02 times 10 to the 23rd for 1 mole, 1 dozen is 1.2 times 10 to the 1st. It's 12, right? So keep that in mind. You know, you could even define a baker's dozen, right, as 1.3 times 10 to the 1. So even though it just sounds different, sounds fancy, that's all it is. It's a shortcut. Okay, one other type of units that we're going to use for some aspects of environmental engineering would be really the number units, number of germs per volume. And that's going to be something like a plaque forming unit for viruses or colony forming unit for a bacteria. And a lot of times you'll see a description of, let's say, 99% of germs killed by this product. And really what that's comparing is for one specific type of germ. They didn't try every type of germ in the world. What they did was they took one specific type and said, okay, can we kill 99% of those specific type of germs in 10 minutes or whatever their test is? And so that's how they come up with that number. So we'll dive into these details more once we get to the kind of biological side of things to talk about how we describe bacterial concentrations and how we know or understand how many bacteria are actually living or perhaps in the water or in whatever media we're looking at. One of the things we'll do with that, just to elaborate a little further, is we can talk about them in terms of logs. Again, we'll get into these details a little more later, but you can describe this as like a 3 log reduction means it's like 10 to the minus third change, or 3 decimal places. So that's, each log is like 1 decimal because it's a log base 10, right? So log base 10 is 1 decimal place. That's what we talk about, that's what we mean when we describe something was 2 log, reduced by 2 logs or 3 logs or whatever. Okay, so coming together, putting these things together, and again, this is a big overview. We're going to go in depth in each one of these pieces, so don't mind if I've gone too fast. We're going to come back through these pieces. Hopefully what you'll recognize is you've seen a lot of these concepts, but you may not have put these together, put the math and put the chemistry and put the physics into one place together like we're going to do in the class and in this major. So the very simple description of a mass balance is we have some rate at which something is going into a volume, and we're going to say this volume, we'll have a control volume, we'll call it, is this circle, and we're going to have some rate at which stuff is entering, and that'll be our input rate. A lot of times that's going to simply be a flow of water or air into some chamber in an engineered sense. You could also think of this in terms of like just a natural atmosphere sense. You could think of a cloud as a parcel of air, or think of a pool of water in a river as sort of a chamber. You can do these in a lot of ways, but in engineering, a lot of times we'll have a reactor in place. So then we have some volume in here, and in that volume, we might have a growth rate. So maybe things are growing in here. Maybe we also have a death or decay rate. And then we have some output rate, perhaps. And I instinctively started writing Q there because we usually describe our flow rates with Q. So if we had an output rate, And maybe we don't have every one of these, but we could have every one of these. And then our mass balance is really trying to understand the accumulation rate. Again, we'll go through more depth into this. We'll take a slower approach, but I just want to give you a kind of a basic understanding that what we're looking at is how much of our stuff is accumulating inside this bubble. How much of this chemical or this bacteria or this pollutant or whatever it is, how much of it is accumulating inside this little circle? Because if we have a lot going in and we separate it so nothing goes out, there's maybe no reactions, then we're accumulating more and more stuff in the bubble. If this is our savings account, well, we want to be accumulating money typically and having a faster input rate than we have output rate. So you can see very clearly that for different areas of our lives, sometimes we'll want whatever's happening inside there to grow, sometimes we'll want it to decay, but to model it, to describe it mathematically, we need to know the input rate, the growth rate. In a bank account, that would be your interest, if you have a positive balance. Output rate, so this would be your income, spending, interest, or maybe if it's a loan, that's a decay rate where you're owing interest. And you can then find your net accumulation rate. And in engineered systems, a lot of times we actually design them so that the net accumulation is 0, and that makes our whole mass balance very simple to solve, as we'll see later in the semester. And so that would be what we call steady state. We're operating in such a way that even if we have some reaction happening, we're neither accumulating nor in a positive direction nor in a negative direction. It's just staying the same. Maybe it's a constant removal of stuff, but we have more coming in, less coming out, and some being destroyed inside. That's your typical wastewater. You have high strength wastewater, there's a bunch of junk in it. You've got bacteria growing that's destroying or eating a lot of the bad stuff. And then your discharge has less bad stuff because your bacteria ate it. So you in terms of the bad stuff, you have a high input rate, a low output rate, but also a decay rate inside so that you can achieve that output rate, that low output rate, without having more and more junk in this reactor. Because if you just gain more and more junk in the reactor, eventually it's going to spill out or whatever. We need that material balance, and operating in steady state oftentimes is very handy. So we'll look at steady state and non-steady state mass balances, and we'll get into really what that means mathematically. Okay, so here's a simple example from a different textbook, one that I've used for my other class quite a bit. And it's just a little example of a very simple mass balance. So feel free to try this on your own. This type of problem in particular is one that you probably have all of the tools at your disposal. You could probably solve this on your own without even hearing a thing about this class. However, what we're going to do, and what I'll do with you once I'm back with you in person, is walk you through this problem and make it a very explicit process. And my goal here is so that we can help you understand, go beyond just your intuition that can probably solve this one if you put your mind to it, and give you a method to solve it so that you can do this one and any other mass balance that comes your way, even if it's more complicated, or maybe it has 2 outputs and 1 input instead of 2 inputs here and 1 output. So what we see here is 2 streams mixing. We're given some control volume, and we have different concentrations, different flow rates coming in, and what we want to know is what's the flow rate going out and what's the concentration going out. So I'll leave you with this, and when I'm back in person with you, we'll pick up here, we'll solve this together, and we'll go from there. So again, thank you for your patience. Sorry that I can't be there. I'm sure that the first week of classes is always kind of hectic anyway, so hopefully you enjoyed the flexibility in your schedule this week. With that, I'm looking forward to meeting you Tuesday when I'm back. Bye.